Okay, everyone, so here's video attempt lesson number 1 here on gases. I'm going to be giving you guys some notes and posting it on Google Classroom later today. So hopefully you'll be able to see that. Hopefully you can see the whole picture here. Okay, so gases, there's 3 really important factors when it comes to gases: the temperature, the pressure, and the volume, and they're all interrelated. Now, the temperature and volume of things we've talked about this year, but we haven't really talked about pressure yet. So I'm going to get into that in a second. But let me just quick review temperature for you. Volume is how much space something takes up, whether it's solid, liquid, or gas, even plasma. The volume when we're talking about gases and liquids will be milliliters and liters. I don't care which one you use as long as you're using the same one for both things. Okay, now, temperature, we have the scales get connected this way. So when you hear or you look on your phone and it says it's going to be 70 degrees out today, that 70 degrees, of course, is 70 degrees Fahrenheit. We're not going to use Fahrenheit at all, okay? And when we use an equation for any calculation, you have to use the Kelvin temperature. That's really important. The reason for that is Kelvin doesn't have any negatives. If you try to plug in a Celsius temperature and you end up with it, like say it's cold, say it's -5 Celsius. -5, you plug that into an equation, you're going to end up with something like a negative volume. And negative volume wouldn't be possible. That would be like, I might have used this example in class. Say you brought 17 pianos into my classroom, and then all of a sudden there was more room in there. That'd be like negative volume. That wouldn't be possible. Okay, so it's very important that you use the Kelvin temperature when you're doing any calculations. It's very simple. If the temperature is 30 degrees Celsius, you add 273, and that would get you the Kelvin temperature, which would be 303 Kelvin. Okay, going backwards, if you have 303 Kelvin, subtract 273, and you would get back your 30 degrees Celsius. Now, it also works for negative numbers in Celsius. If the temperature is -10 Celsius, -10 plus 273 is going to equal 263 Kelvin, but that's still a positive number. So when you plug it into an equation, it'll end up being positive. Okay? And plug in 263 here, subtract 273, you'd end up with -10. So temperature's not really that bad. Because if you get to absolute 0, which is 0 Kelvin, you can't get any colder. It's like the coldest possible temperature, right? That's when all molecular motion ceases. Okay. Anyway, but pressure's a little bit different. Pressure is the force exerted upon something. So think of it like a sponge, if you will. If I had a sponge here and I increase the pressure, I'm pushing it down, the volume of the sponge is going to get smaller. But if I pull that pressure back, the sponge will start to, increase back to its normal size. It's how gases work. Gases can be compressed, like in a CO2 tank or something like that. Okay, so these are the common units of pressure that we're going to use. The first one is the most common. This is ATM, which is the abbreviation for atmosphere. Like 1 atmosphere of pressure would be like the standard pressure that we're all under. That is the equivalent to 1.013 bar. Again, still pretty close. There's like millibar and all this other stuff. But these two are equal. Now, there's another unit of pressure called the millimeters of mercury, which is mmHg. Hg is the symbol for mercury. It's a hydrodrome in Latin, right? And it's sometimes called torr, and it could be a capital T. And that was named after Torricelli, I believe, who was the inventor of the barometer. Then the one over here, we have 101.325 kPa. That means kilopascals. Don't worry, you'll be able to use your metric converter. Or 101,325 pascals, PA. Now, Pascal was a scientist, but he was also a poet, and he struggled a lot with his science and theology. But anyway, so they named that after him. Now, the way that these units work are kind of like what we did in when we were doing conversion factors earlier in the year. How many miles per hour is this car moving? If it's moving, 105 meters per second, something like that, all right? So The first thing I want to do is just do a quick refresher of how we do conversion factors. These things here, this is like one big conversion factor right here. All of this. All of these are equal. Kind of like 1 hour is equal to 60 minutes. All right? But it's also equal to 3,600 seconds. So we could say that 1 hour is equal to 60 minutes. And 60 minutes is equal to 3,600 seconds, so therefore 1 hour must be equal to 3,600 seconds, right? Same thing here, these are all equal. Let me show you how they work. So in the notes that I'm gonna post for you, it says 885 mmHg, millimeters of mercury. It says you wanna convert that to kPa, which is kilopascal. Okay, so it's pretty simple. So you start with the 885 millimeters of mercury, and since that's our starting number, we'll just put that over 1. Remember when we did all that? Especially with the mole, that came in pretty handy. Okay, so we want to change it to kPa. This is according to the note packet. So we want to get it to this. All right, which means that's what I'm looking for, so I'm going to have that on top. And the thing that I have, I'm going to put on the bottom. As I'm just going to set up a conversion factor. Well, let's see. 101.325 kilopascals is equal to 760 millimeters of mercury. These two things are equal. All right, so all I'm going to do is I'm going to put the 101.325 kPa on top. And I'm going to put the 760 millimeters of mercury, the mmHg, on the bottom, so it'll kind of look like that. All right, now look, the unit that's on the top and the unit that's on the bottom are going to cancel because they are like units. All right, now to get my final answer here, I just have to do 885 times 101.325 and then divide by 760. Now, I did this a little bit earlier, and I got an answer close to, but not exactly, 118 kilopascals. So that would be the pressure that is the equivalent to 885 millimeters of mercury. Okay? All right, now let's take a look at another one. There's ATM and bar. Why don't I do the one where it says convert the following to bar? So I will go 213,456 pascals. Let me write that one down. All right, so we got 213,456 pascals, and I'm going to put that over 1. So it kind of will look like this. Okay? 213,456 pascals. Did I get that number right? Okay, I got that number right. All right, now it says, for this one, it says convert the following to bar. All right, so I want to go from here to here. Well, just remember, these are all equal to each other. Okay, just like one day is 24 hours, right? Okay, so we have one ATM is that many bar, that many bars, that much millimeters mercury, and that much kilopascal. Okay, so I have Pascal right there. That's on the top, so I want to put that on the bottom. And I want to put the thing I'm looking for on the top. I'm looking for bar, according to the question. So I'm going to set it up like this, right? So I'm looking for bar. I'm going to put that on top. 1.013 bar. That's why it's called a barometer, to measure pressure. And 101,325 pascals on the bottom to convert them out will kind of look like that. All right, I'm starting to run out of room. Okay, but the Pascal PA here and PA here will cancel out. So to get this answer, you're going to do 213,456 times 1.013, and then we're going to divide by 101,325. Now, I did this earlier also, and I got an answer very close to 2.13 bar, and I box that off, okay? And there is how I get my units to convert, Okay? We'll do a couple more of these. I will, maybe I'll do them and post the answers, but I want you to try to follow along. The only thing I'm really worried about, everyone, is that you can follow me on the first page of the notes, okay? And then what we'll do is we'll see what happens to a gas when we increase the pressure and when we increase the temperature, and we'll do some calculations. And we're going to take a lot into consideration that, like, all gases behave in this perfectly ideal fashion, even though they do not. Okay? All right, but that's a little brief crash course. I'm going to give you guys some time to look this over. I will also work out the first couple examples in the packet. All right? Hopefully this goes well, and it looks like I'm not going to see you guys for the rest of the year, which is definitely a shame for you. Okay? Take care, guys. See ya.